Hello, am I audible? पूछ रहा है, am I audible? Okay. And am I visible on the camera? So we will wait till 6:05 and then we will continue with the session. So let's start. It is 6:05 now. Hello all. Welcome to week 8 of live session of solid mechanics course on NPTEL. My name is Manoj Shikhar. I'm one of the TAs in this course. I'm a PMRF scholar at IIT Delhi. I work in the Department of Applied Mechanics, and uh, I will be taking these sessions on every Tuesday from 6 to 8 p.m. More about myself. I've done my BTech and MTech from IIT Kharagpur. And before I start this session, I'd like to declare one thing. Uh, in this session, we generally try to solve some numerical problems or clear your doubts regarding the topics. So while asking the question, please keep in mind that we will not be able to help you with the questions which are currently active, uh, which are currently a part of active assignments. Okay, so kindly refrain from asking questions from the assignment. I will try to solve as many problems as I can within this time frame, and I will try to clear your doubts. So in week 8, the topics which have been covered are extension, torsion, inflation in a hollow cylinder. So mainly this topic has been covered, and in, while covering this topic, various kinematic constraints like which satisfy axis symmetry or axial homogeneity, they have been discussed. And then later on, sir solved some problems in the last lecture. So also, if you want to access the notes of this course, APL, so you can go to this link. This is the link for APL 104 course. So this is the same course at IIT Delhi, which is getting published at on NPTEL. So the lecture notes will be similar. So you can download the lecture notes, PDF version of lecture notes from this website. So just for a quick recap, what was covered in this week. So there were three modes of deformations which was discussed. Okay. The So what is extension, torsion, or inflation? So when you stretch a body, that stretching is called extension. Okay. On the other hand, if you try to rotate the body by applying torque at the end planes, you will see that different cross section of the body will rotate rotate differently. So this is called twisting or torsion. Okay. And the third case is inflation. In that, what happens? You have a body, you apply pressure inside. So if you apply pressure inside it, the body will inflate. So that's why the name inflation. Also in this course, the stress components, they are proportional to strain components, and strain components are proportional to displacement components. So we are assuming that the governing equations, they will be linear in stress components, and they will subsequently become linear in unknown displacement components also. Okay. So what was the problem definition? Suppose our goal is to find all the displacement and stress components induced within a cylinder. We are starting with a hollow cylinder. We are subjecting it with axial loading F. We are applying a torque T at the end, and we are also applying the internal pressure P. And we want to know that what will happen to the body. Okay. Now, we already know that we have many unknowns, like we had 9 unknowns. If we assume that the angular momentum balance is happening, if we invoke that condition, total 9 unknowns remain with us. And what are those 9 unknowns? Those unknowns are displacement fields, like in this case, UR, U theta, UZ, and stress components. So if the stress matrix is symmetric, there will be 6 independent components. Okay, 3 diagonal components and 3 off diagonal components. So total 9 variables or 9 unknowns are there. Now, after that, what we did, we simplified our displacement, or we simplified our displacement basically assuming various things. Now, initially, when we start with, for any problem, when we start, we are forced to assume that the displacement components will be a function of r, theta, and z, because r, theta, and z, they are independent components, independent variables, and we don't know how our displacement will be. So in this case, this u is basically a function of r, theta, and z. After that, we realize some things and we reduce our problem. We try to figure out that if UR or U theta or UZ will be dependent upon R, theta, Z, or it will depend upon only R or only theta or only Z. Okay. So the first assumption is axis symmetry. This assumption leads to displacement fields which are independent of theta. Okay. So our UR, U theta, and UZ, if we invoke axis symmetry, they will only become the functions of R and Z. So you can see the result was UR is a function of R and Z, U theta is a function of R and Z, and UZ is a function of R and Z. Axial homogeneity. So suppose this is a cylinder. Okay, this is a cylinder. We are assuming that any section we take in this, suppose this is the Z direction, this pointing, where this pen is pointing, this is the Z direction. Any cross section we take in Z direction, it will have similar UR. So this is called axial homogeneity. Okay. So as a result of axial homogeneity, our UR, it reduces to be a function of R only. Then we consider no warping of a cross section. So what does warping mean? Suppose if I have a cross section here. Suppose I cut a section. Okay, I cut a section here. So I will have some circular cross section there. So if I allow the warping of that cross section, each point on that cross section may have different Z component. Okay, but we don't want that. We want that all the points on a cross section, they will have same Z component. So that's why UZ becomes a function of Z only. It does not depend on R. Okay. So till now we know that UR is a function of R only and UZ is a function of Z only. And U theta, it is a function of both R and Z. And after doing some mathematics and thinking, in class we derived that U theta will be alpha Z into R, where alpha is very small. Okay. So this is the form which we get for our displacement fields. Now to find the strain matrix, we simply put the displacement fields in the expression of the strain matrix we found last week, and we get strain matrix as UR prime 0 0 0 UR by R, alpha prime R by 2, 0 alpha prime R by 2, and UZ prime. Okay. So you can see that only the shear strain of gamma theta z will arise due to torsion. Other shear strains are zero. Okay. Now we already know the stress strain relation for the stress strain relation uh, for an isotropic material. And so here we have just replaced the expressions of epsilons in terms of the displacement fields. So you get these stress displacement relations. Okay? And here U prime means the differentiation of that quantity. Okay. So U prime R is del U by del R. Del U R by del R. So we have discussed about displacement. So we have discussed about the strain matrix, and we have also discussed that what is the relation between stress and strain. Okay, just give me 1 minute. Anyways, so we know the equilibrium equations in cylindrical coordinate system. They are given by equation number 12. And when we substitute these stress relations from equation 11 in equation number 12, we will get this form of equilibrium equation. Okay. Now, one thing to remember is alpha is just a function of z. Okay. Uz is just a function of z, and ur is a function of r only. But u theta is a function of z and r. And it is assumed that u theta varies linearly with r. That's why alpha z times r has been taken. Now, then we took some examples that how do like what will be the values of BR or B theta or BZ or any other things? How do we decide that? So one example was that we have a rod or we have a cylinder and we have kept it vertically. So in that case, if we assume that the vertical direction is Z direction, then BZ will be minus rho g and B theta and BR will be 0. What if the cylinder was rotating? In that case, we will take that acceleration of the cylinder will be minus omega square r and A theta and AZ will be 0 because it is just rotating. So we will have only the centripetal acceleration. Suppose if we in this example there was some alpha, the angular acceleration was also present. So let me say some other. Let us denote that by phi because we are already using alpha for some other thing here. So if we had some angular acceleration also, then A theta would have been alpha into r. Okay. Sorry, phi into r. Phi is the angular acceleration of the body. So if we substitute that, we will get this equation. Now, what if the cylinder which we took in the first example, what if this was kept horizontally? In that case, the gravity will act in a direction perpendicular to z. So it will have two components, one in BR direction, R direction, in one in theta direction. So that's why we will get BR and B theta. And one problem was zero gravity and statics problem. So in this case, the body forces will be 0 and all the accelerations will be 0 because zero gravity is there. So there is no body force and statics means there is no acceleration. So our equations, the equilibrium equation will reduce to equation number 19. And from here you can see that one thing is apparent, that sigma zz will be constant with respect to z. That means that sigma zz will be a function of r and theta only. Alpha double prime is 0. Okay. So this is what we get from the equilibrium equation in the theta direction. And this is the equation we get in the radial direction. For this case, we get u theta equal to omega by L into Rz, where omega is the total rotation. So suppose if this end is rotated by omega by 2 and this is rotated by minus omega by 2, then the total rotation is what? Omega. And it is assumed that along the length, maybe I should open the journal now. Suppose this end is rotated like this and this is rotated like this. So phi will be, sorry, what is they have taken? Anyways, so this is like linear variation. At this point, at z equal to minus L by 2, we have phi equal to omega by 2 with negative sign. And here at z equal to L by 2, we have phi equal to omega by 2. And we are assuming that in between point and B, A and B, this variation is linear. So what will be phi at any z? It will be omega by 2 minus omega by 2 divided by, here z is L by 2 minus L by 2 into z plus some constant. Now we can put z equal to minus L by 2 here, and we will get, this is what, this is minus omega by 2. Okay. So putting z equal to 2 there, what we will get? So we have an equation phi z equal to omega by L into z. Now this phi z is actually alpha prime z. Should have written it earlier only. Straight. Write it as alpha z. That will be better. And what will be alpha prime z? It is omega by. That is what was written there. And to find u theta, we just need to multiply alpha z with r. So from here, we will get I hope this is clear to all of you. Now, since now we know the expression of u theta, we could put that in the expressions there, and we tau theta z comes out to be g omega by L into R. Now, from this equation, we know that sigma zz is independent of z. Okay. So this term actually depends upon z in the case of sigma zz. This means this term is constant. So u prime z is a constant. So from here, we know that u prime z is a constant, or epsilon 3 was a constant. When we say u prime z, this is del u z by del z. Okay. Differentiation of u z with respect to z. Here, del u prime r is del u r by del r. Keep this in mind. If we say u prime z is a constant, that is say epsilon. So this means that uz is epsilon times z. Epsilon times z plus some constant c. Okay. And u prime z is what? It is actually the axial strain in the z direction. Now, if we assume that uz is 0 at we assume uz equal to 0 at z equal to 0, then in that case, this constant c will be 0. Okay. So uz reduces to epsilon z, which was taken in the class. So while considering uz equal to epsilon z, it was assumed that uz equal to 0. So that's why I pointed it out that many times I've seen students making this mistake. They drop these constant terms after integration. In this case, in class, we dropped it because we assumed that at z equal to 0, our uz is 0. Okay. But there could be some problems where we can't take c equal to 0. So just keep this thing in mind so that you don't make any mistake in the exams. And if in exam you get a condition where this is valid, that uz equal to 0 at z equal to 0, then okay, use this formula, uz equal to epsilon z. But keep this in mind. So Later on, we moved on to derive that what will be the expression for UR, what will be the expression for sigma R or sigma theta, and so on. So now let's move on to solve some questions related to this topic. If till now anybody has any doubt, they can ask me. Okay. So question number 1 is 50.8 diameter steel tube. Okay. With with a wall thickness of 1.27 mm. Just fits in a rigid hole. Find the hoop stress. If an axial compressive load of 1424 kg is applied. Okay. So in this question, there is a hole present. This hole is present, and what they did was a steel tube was put in here, and it is put like so that it just fits. Okay, there isn't much gap in between the hole and steel tube. It is just a fit. Now what they are doing, they are compressing it. The load is 1424 kg. They're applying 1424 kgs. They're telling us to find the hoop stress. Now, at first glance, it will look like that this is a uniaxial loading problem because we are just applying a compressive load. But if you look at this problem carefully, you will realize that this is not an uniaxial loading case. This is a biaxial loading case. How? So you are applying some load in the axial direction. Now your body is getting compressed. But since this hole is rigid, they have given rigid hole. Okay. What does rigid hole mean? It won't change size. Okay. The size of this hole will remain the same. So this body, it is fitted in this hole and we are compressing it. But the size of this hole will not change. And this hole is immovable. This won't move. So what will happen? When we compress the body, there will be some deformation in the direction of lateral. There will be some lateral deformation, but the body is not allowed to move in that direction. So the walls of this hole, they will apply some pressure or some traction on this body. We don't know the value of traction right now. So what will happen is, let me draw it. So the actual problem is what? It is getting compressed axially. And in lateral direction, it will have some pressure or traction, whatever you call it. But since it is compressive, so I was calling it pressure. There's some traction. Traction in the lateral direction. Okay. This is the compressive load. So this is a biaxial loading. You can see that the hole is actually applying uh, traction on the body. So there are a few things which we can say about the deformation map. So the first thing is u theta will be 0. There will be some uz. Okay. And there will be some ur. And what do we need to find in this question? We need to find that what is sigma theta theta. So let us first find out what is sigma zz. So sigma zz is total force divided by total area. So here it is a tube. So it's like a tube. because they have given some thickness also. Is it tube? So area of the tube is what? Pi d square minus a small d square by 4. Okay. So this is what? F by pi d plus d by 2 into d minus d by. And what is this d minus d by 2? This is thickness t. Okay. So this is t. So a few things. Let me draw the cross section. How will it look? So this is my small d. And this is capital D. And this thing here, this is thickness. So what will be relation between small d and capital D? So capital D will be what? Small d plus t here and t here. So 2t. So d minus d by 2 will be what? T. The thickness. Also, what will be d plus d? This will be d plus d plus 2t. This means 2 times d plus t. So let's replace this in the expression here. So this is nothing but f by pi t into 2d plus t divided by 2. So we will get sigma zz equal to f by pi into t into d plus t, where d is the internal diameter. Here there is one assumption that sigma zz does not vary with thickness. Okay. That is sigma zz only depends upon. It does not vary in the r direction. Now in class, we have already seen the expressions for sigma rf. What were they? So I can't derive these expressions again because it will take a lot of time. So these were the equations. So I'm just writing it them here. Okay. And how do we obtain the values of A and B? So values of A and B, these are also known as integrating constant. Okay. So these were the constants which came from integration. These will come from the boundary condition. Okay. This will be obtained through boundary condition. Now, what are the boundary conditions for this problem? If you look at the tube in this case, this tube is loaded here, axially loaded here. And it is loaded from lateral direction also. But there is no internal pressure in this tube. This was wrong because the force cannot act in the vacant place, right? So I will just correct this figure quickly. The force will act on the material, right? That was vacant place where earlier it was sound, so it was wrong. This. So let's move on to the problem. So the boundary conditions are boundary conditions are first one is sigma RR at R1 equal to 0. Why is it 0? Because there is no internal pressure. Internal pressure. Nice. But we can't say anything about sigma RR R2. Okay. We can't say it is equal to 0 because our constraining pressure is unknown. What is the constraining pressure? The pressure which is getting applied on this body on its lateral surface by the hole, by the wall of the hole. Okay. So this was the traction boundary condition. So what was this? This was. Traction boundary condition, right? BC means boundary condition. Now what will be the displacement boundary condition? So at the end point, we know that UR will be 0. Why? Because the last point, this point is rigidly connected with the rod. Sorry, not rigidly, it is a fit with the hole. Okay. So this means these 2 points are at the same point. And when our body will deform, this point cannot go up. This point cannot go up. So you are at r equal to 2. You are the radial displacement at r equal to r2. This will be 0. Okay. And we know that we also have the expression of UR from our course. We know what is UR. So UR equal to CR by 2 plus D by R. Okay. So if we put R2 equal to 0, sorry, U at now we need to find this is a function of R. Okay. So remember this. So UR at R2. This will be CR2 by 2 plus D by R2 equal to 0. So from here we will get a relation between C and D. So C will be minus 2D by R2 square. Or we can write D equal to minus C by 2 into R2 square. Okay. And we also know the expressions of sigma R. So what are the expressions of sigma RR in terms of UR? Okay. So this is lambda UR prime plus UR by R plus UZ prime plus 2 mu UR prime. So sigma RR will be, if you solve it, so you will get now we know that this also has a form A by 2 minus B by R square, right? So from this two expression, we can find actually relation between A and C. So this is what? This is A by 2. And this term here, this is, sorry, it should be A plus B R square. This whole term with negative sign, this is B by R square. Okay. So what do we have? We have A equal to Let's write the form as this term is b by r square. We will assume that a by 2 minus b by r square. Hmm. Here I made a mistake. It should be lambda plus mu. Okay. So I just wanted to show you that we have taken the form a by 2 plus b by r square earlier. So I'm moving back to the same form so that you're not confused. So here you can see that this part is a by 2 and this minus 2 mu d by r square is b by r square. So from here we will get that b equal to minus 2 mu d. We also have another expression u prime z. This is equal to 1 by e into sigma zz minus nu times sigma rr plus sigma theta theta. Okay, because u prime z is strain in the z direction. And we also know one thing, that sigma rr plus sigma theta theta, this is constant. This equals to a. So we can replace this expression here. So this will be what? 1 by e into sigma zz minus mu a. So we can replace mu prime z here. We can replace mu prime z here, and then we can find what is the relation between c and a. C as a function of a, and we can also find d as a function of b. Okay, so maybe I should write it here. Let's not skip it. So after putting this, what we will get? We'll get a by 2 equal to lambda plus mu into c plus lambda times sigma zz minus mu a by e. Okay. So from here, a by 2 minus lambda by e sigma zz plus lambda into mu a by e equal to lambda plus mu into c. So from here, what we'll get? We'll get c equal to and for d, we will use from this equation. So we will have d equal to minus b by 2. Now, how do you obtain a and b? This is a subjective problem, so it is taking a lot of time. I hope I will be able to do two more problems. So to obtain A and B, we will use sigma RR at R1 equal to 0. So A by 2 plus B1 by R square, sorry, B by R1 square equal to 0. So from here we get A equal to minus 2B by R1 square. The other expression is UR at R2 equal to 0. So here I've already found out D was minus C by 2 R2 square. D equal to minus C by 2 R2 square. So other method could be minus A by 2 R1 square equal to V. So we know the expression of D, we know the expression of C. We have to replace, so you replace D from here, minus B by 2 mu equal to minus C by 2 into R2 square. And we can also replace the expression of C here. So basically minus A by 2E into E plus 2 mu lambda minus sigma ZZ lambda by E into R2 square by. So this is one of the equations between A and B. This is another equation from A and B. So if we solve these two equations, we will get on solving 1 and 2, we shall get A and B. Now we can do one more thing. We already have A and B now. So if we also know that sigma RR equal to A by 2 plus BR square. So now if we put R equal to R2, then we shall be able to find the unknown pressure. We shall be able to find unknown pressure being applied by hole. Okay. And also if you simply put the, so also you also know the expression of sigma theta theta now. Sigma theta theta is what? A by 2 minus B by R square. So if you put A and B, put A and B here, and you will get the sigma theta theta. Now you can put the numerical value yourselves. I'll just write what you have to write for the numerical value. So F is 1242 kg. You need to convert it in Newton. You have been given D, small d. I think they have given it to be 50.8 mm. So R1 will be 50.8 by 2. This is 25.4. They've already given you thickness equal to 1.27 mm. Okay. So put those values and you will be able to find the values of A, B, and so on. Okay. So do that yourselves. They've given you a steel, so you can find the values of lambda and mu online. You can search this. Or you can consider these values. Mu equal to 0.3, E equal to 210 GPa. So from here you can also find, if you don't want to do this, you can find the values. Find lambda and mu, assuming steel to be isotropic. So in this case, actually, the data of E and nu was not given. Okay? In the question, it was not given. So, and also you were not given what are lambda and mu, the lambda is constant. So here, suppose if you face this problem in the exam also, you assume some possible values, like some, for example, if it was an aluminum tube, if you take E equal to 210 GPa, it will be wrong because its E is around 70 GPa. So you have to have some idea that in which range this E will fall or what should be the value of nu. Okay. And for isotropic material, we know that we need only two constants. So if we know E and nu, we can find what will be lambda and what will be mu. So in this question, you need to remember that, okay, how is lambda is related with E and nu? How is mu related to E and nu? Okay, so keep that in mind. So you can solve this problem like value putting you can do yourself because I have to solve other problems also. This is a subjective problem. It will take long time. Okay, so another question is, so we have a set of gears with us. Okay, so they have given you 4 gears and the gears they have been applied with some torque. And you know the length. So this is 2 meter. This is 3 meter. And this is. So the question is, an aluminium shaft with constant diameter of 25 mm. Sorry, 50 mm, not 25. 50 mm is loaded by torques. Okay? Is loaded by torques applied to gears attached to it as shown in the figure. They're given you using G equal to 28 GPa. Determine the relative angle of twist of gear A related to gear D. Okay. So the nomenclature is something like this. This is gear D, this is gear A, this is B, and this is C. And they want you to find what will be the relative angle of twist. So that is basically omega A minus omega D, or omega D minus omega D, omega A, if we want to know the total angle of twist. Okay. So first we draw the torque diagram. So how do we draw the torque diagram? So in this, you have to first assume a direction which will be positive. So I personally choose the counterclockwise or the right hand rule. Okay. If a torque is acting in a counterclockwise direction, I take it positive. If it is acting in a clockwise direction, I take it negative. So if I turn my right hand and the direction of torque is coming in the direction of this thumb, I will take it as positive. So the first torque, which is acting on gear D, it is 800 nanometer in clockwise direction. Okay. So 800 nanometer is in clockwise direction. So it is minus 800 in my torque diagram. Okay. So torque diagram. So first I will mark all the points here. The points are basically D, C, D, and A. Okay. So between D and C, we have minus 800 Newton meter. So this is minus 800. Now at C, there is a sudden jump. And after C, there is no other torque. So that sudden jump is of 1100 plus 1100. It is in counterclockwise direction. Okay. So plus 1100. So from minus 800, we have to add plus 1100. So this will come somewhere here. And from between C and B, there is no other torque. So we will have the constant value. And this value is 300 Newton meter. This was 800 Newton meter. Okay. Then again, we have a torque of 900 Newton meter in clockwise direction at B. So from 300 Newton meter to we have to move minus 900. So 300 minus 900 will be minus 600. So somewhere here. And in between B and A, there is no other torque distribution, so it will remain a constant line. And at A, we have plus 600 Newton meter. So our torque will become, our torque line, our torque diagram will converge at A at 0. Okay. So this is minus 600 Newton meter. So this is our torque diagram. And this length is 2 meter. This is 3 meter and this is 2 meter. Okay. We also know the formula of omega. So what is the formula of omega? This is TL by GJ. Okay. So TL by GJ. Now, if you look at this torque diagram, you will see that in between D and C, torque is constant. In between C and B, torque is constant. And in between B and A, the torque is constant. So we can also write omega AD as omega DC plus omega CB plus omega BA. It will be omega DA actually. Okay. What will be omega AD? That is basically omega A minus omega D. So how I was able to write this, I will show it here for this part. How did I write omega A minus omega D? Okay. So omega AB is omega A minus omega B. This is omega AB plus BC. Omega BC is what? Omega C. Uh, so here actually it will be omega D minus omega A. Okay. Omega AB is what? Omega B minus omega S. So sorry for that. Then omega C minus omega B. This is omega CB plus omega D minus omega C. This is omega DC. Now, if you look at it, this term will cancel with this term. This will cancel with this. So in the end, what do we have? We have omega D minus omega A. So I can write omega AD equal to omega. I think I have done some mistake in writing the question. It should be angle of twist of gear D with respect to A. So here it should be D with respect to gear A. Okay. So omega AD is what? Omega AB plus omega CB plus omega DC. So if we add the individual angles of these zones BA, CB and DC, we will get what is the total relative change in the angle. Okay. So in between omega AB, torque is constant. You can see minus 600 Newton meter. Length is 2 meter. And since the material as well as the diameter of this rod is not changing, this shaft is not changing, the bottom part GJ is constant for all of them. So I can also write it as TAB LAB by GJ. Just for the general case, I will write GAB and JJB. Then I will replace it later on. Plus TCB LCB by GCB JCB plus TDC LDC by GDC and JDC. Okay, before doing that, note one thing that the total torque was 0. Okay, the total torque applied on the body, if you add all these, This was 0. 8 plus 9, 17. 11 plus 6, 17. Okay, so 1700 minus 1700. This was a static case. That's why we were able to use this formula directly. Omega equal to TL by GJ. Otherwise, we would not have been able to use this. So keep this in mind. I will write a note here. Keep in mind that here TA plus TB plus TC plus TD equal to 0. That is static case. Thus, it was a statics case. Okay. Hence, we were able to use omega equal to TL by GJ. Now just to find the numerical value, you can put TAB equal to minus 600, TCB equal to 300, TDC equal to uh, minus 800, all in Newton meters, Okay. LAB equal to 2 meter, LCB equal to 3 meter. It is given in the question. LDC equal to 2 meters. And GAB equal to GBC equal to GCD, because the same material of shaft, the shaft of same material is used, and I think it was 28 GPa, something like that. 28 GPa. Okay. You can also find the polar moment of inertia J by using this formula, pi d to the power 4 by 32. Here d equal to 50 mm, given in the question. Okay, given in the question. So you use these formulas, you put all the values here, and you will be able to find what is omega AD. So I hope this question is clear to you. They have given you 50 mm. Okay. So suppose if they had asked what is the angle of twist of gear A relative to gear B as a gear D, so that will be negative of this thing. Okay, because you will have to find there sigma A minus sigma D. You will have to find this there. I should write it here actually. Angle of twist of gear D relative to gear A. For this, make a box. This is what? Angle of twist of gear A relative to gear. So depending upon question, you have to write the answer, but I have shown you the procedure. So let's take a break of 5 minutes and then I will continue again. Hello. Yeah, so welcome back, all of you. Uh, let's continue the class. This will be probably the last question of this week. So the question is, they have given you a solid disk of radius r, and there is a hollow disk of inner radius r1, inner radius r1, and outer radius r2, outer radius r2. Okay. R is greater than r1. So the solid disk, its radius is greater than the internal radius of the hollow disk. Okay, this is given. R is greater than R1. So solid disk is shrunk fit. Okay, shrunk fit together with the hollow disk. Now you can see one thing, that the radius, the radius of the solid disk is larger than the inner radius of the hollow disk. So the to fit the solid disk in the hollow disk, we have used a technique called shrunk fit. Generally, it is done by heating. So you heat the outer, the hollow disk. It will expand slightly. You will fit the uh, solid disk, and then you will cool it. After cooling, it will shrink. Okay. So in that case, there will be some residual stress there at the interface. So that was the procedure I described. It is one of the methods. So what do we have to find in the question, and what are other things which are given? Okay. So so first assumptions, like the assumptions which are given, assume no external pressure. No external pressure is applied on the outer hollow disk. On the outer hollow disk. And you have to also assume and no axial displacement is allowed into disk. So they have given you that uz equal to 0 in the two disks. Also assume that both disks are made of same material. Both disks are made of same material. So their properties will be same, like EG and other things will be there. And one more assumption is only radial displacement, that is UR, is generated in this case. So this is given in the question, generated in this case. You have to write down all the boundary conditions, BC's boundary conditions. So I will write boundary condition in short form as BC's. Okay. So from now on, if I write BC, it means boundary condition or interface conditions. Interface conditions. I will not short form this term because if I write IC, you will be confused later on. ICs are generally used as initial conditions in differential equations or in other subjects. So I'll write interface conditions required to obtain variation in radial stress, sigma RR, okay, in the two disks. So you have to mention what are the boundary conditions. This question is pretty good because it will help you to understand how to write boundary condition, how to use it in the governing equation and so on. Question number 2 is solve the governing equations. EQNS means equations and obtain expression for sigma RR. In the two disks. And question number 3 is obtain expression for circumferential slash hoop stress. And fourth one, draw plots for variation of sigma RR and sigma theta theta. Okay, so here you have to find basically sigma theta theta. Now, first thing first. So you have been given two disks. So this is a solid disk with radius R, and this is a hollow disk with radius R1, and this is R2. Okay, so this is the hollow disk, and the assumption is R is greater than R1. This is before shrink fit. Before shrink fit. Now after shrink fit, what will happen? We can consider it like this. Okay, so just think it like this. The final body will look something like this, right? This is my solid disk and this is my hollow disk. Okay. Now, this hollow disk will apply some pressure. Will apply some pressure on the solid disk, and the same pressure will be applied on the hollow disk by this solid disk. This pressure is unknown right now. So here we will have some unknown pressure applied on this. This is my solid disk and unknown pressure is getting applied. Let us denote that by P star. And the other thing is, what will be the new radius? Some other color. This new radius will be R equal to so we are analyzing what will happen after shrink fit. Okay, after shrink. After shrink fit, what will happen? Okay. So let us first see the inner. So the inner part, this solid disk. Okay. So its radius will be different from R. It will not be equal to R because it has been shrink fit. So what will be this? This will be R plus so here I'd like to declare one thing. So UR1 is displacement radial displacement of solid disk. And if I write UR2, this means radial displacement of hollow disk. Okay. So if UR1 is the radial displacement of this solid disk, this is my solid disk. So what will be the new radius? The new radius will be R plus UR1 calculated at the radius capital R. Okay. Keep this in mind. This one is really important. Now, if we try to calculate, if we want to find what is the inner radius now, the inner radius for this hollow disk we had, okay, for it, the inner radius will be, just think about it. What should it be? The inner radius R1. This will not remain R1 now because we have shrunk fitted. So this will be R1 plus UR. Here it should be 2 because we are writing the radial displacement of hollow disk by UR2. Where should it be calculated? At original R1. R1. Okay. So you see the difference here. Our radius has changed and we are taking different functions for radial displacement of solid disk and radial displacement of hollow disk, and we are substituting that function at different radii, basically. Okay, at different radii. Here it is capital R, which is the outer radius or the radius of solid disk simply, and here it is R1, which was the inner radius of hollow disk. So this is on shrink fitting. Okay, so this is on shrink fitting. This was before shrink fit. Okay. And one thing I forgot to make was the external pressure on the, sorry, not the external pressure, the pressure applied on the solid disk by this hollow disk, and we will have this kind of pressure, the same P star, right? P star. So similarly, we will have different functions for sigmas. So wherever this we have superscript 1, it is for solid disk. Wherever we have superscript 2, we have this hollow disk. So sigma RR1 will be A1 by 2 plus B1 by R squared. Sigma RR2 is what? A2 by 2 plus B2 by, what should it be here? R squared. Okay. And this R will be replaced with like capital R or capital R1 or whatever it is. But we here it should be smaller because as a whole we are taking, right? Similarly, from class, we know that the expression for UR will become I'm not deriving these expressions because they have been done in class already. So it will be a waste of time. I'll just give you the steps you can follow for solving these problems. Okay. So let's write in terms of index directly so that we don't have to repeat everything. So AI will be what? Since they are made up of same material, so it will be 2 times lambda plus mu into Ci. Okay. And Bi will be what? Minus 2 mu into Di. So here lambda and mu, they are not written with any subscript superscript because the material for both hollow disk and solid disk, they are same. Otherwise, here also we needed to index like I. Okay. So keep that in mind. If in question they have given you 2 different material, you will have to write here. You will have to write the index here. You will be forced to. Otherwise, you will get the wrong result. Now, question number 1 is what are the boundary conditions, right? So let's move on to boundary conditions are the first one, sigma RR1 at capital R. This is equal to sigma RR2 at R1. This is continuity of radial stress. Continuity of radial stress. And this is basically your pressure P star, whatever you will get. The second thing is the final radius of the solid disk and the final internal radius of the hollow disk, they will be same. Then only the shrink fit will happen, right? So R plus U1R, oh sorry, U1R at capital R is equal to R1 plus this is your shrink fit condition. We have also been given sigma 2 R2 equal to 0 because we have been given traction free condition, right? Traction free condition. So just let me make some changes here. Should be. And the third thing is, and the fourth one is, this is sigma RR1 at R equal to 0 is finite, or UR1 at R equal to 0 is equal to 0. Now the second question. We have sigma RR1 equal to lambda plus mu into C1 minus 2 mu D1 by R square. We have sigma RR2 equal to lambda plus 2 mu into C2 minus 2 mu into D2 by R square. Okay. We know that sigma RR1 0 is 0. So at 0 it should be what? 0. Sorry, not 0, finite. So if we put R equal to 0 in this equation, it will become infinite. This means that D1 is 0. Okay. So this sigma RR1 at 0 will be finite, forces D1 to be 0. So our sigma RR1 reduces to what? Lambda plus mu into C1. Okay. Now we apply this boundary condition, the first boundary condition. Let me change the color of this pen. Sigma RR1 at capital R is equal to sigma RR2 at R1. So from here we will have lambda plus mu into C1 equal to lambda plus mu. Why is it 2 mu here? Into C2 minus 2 mu D2 by R1 squared. Okay. And from here, equation number 2, we have U1 at R minus U2 at R1 equal to R1 minus R. So we have two equations. This is equation number 1. This is equation number 2. And what we can do, we can replace U1. So we also know the expressions of U1, U2. So we can replace them here. So what will happen? T1 by 2 times R plus D1 by R minus. So D1 is 0. So this will not be there. Okay. Anyways, so minus C2 upon 2 times R1 minus D2 upon R1 equal to R1 minus R. So this should be our equation number 2 actually. And we have another boundary condition here. Sigma RR 2 at R2 equal to 0. So if we apply sigma RR2 at R2, so this will be what? This will be lambda plus mu times C2 minus 2 mu D2 by R2 equal to 0. So we have three equations. We have three equations. 1, 2, 3. And three unknowns. C1, C2, and D2. So we can solve for them. Solve for If we solve for them, moreover, they have told that use the equilibrium equation and all. So these equations were derived using equilibrium equation, if you remember the method. Okay. So it is implicit here. I am just using the expressions directly. Okay. Now, since we know the constants, so since we know the constants now, the unknown constants, we can find sigma theta theta. Sigma theta theta, and it comes out to be sigma theta theta 1 and sigma theta theta 2. Okay. And sigma theta theta. So the expression for sigma theta theta is sigma theta theta 1 at R is lambda plus mu into C1. Okay. And sigma theta theta at lambda plus mu into C2 plus 2 mu D2 by R square. So if we plot our sigma and R, you can do it yourself also. I will give you the final plot. So when we plot so this dimension is R and this is sigma. So if we plot sigma RR first, so till this point, it will be a constant value. And the value is lambda plus mu C1. Lambda plus mu into C1. You can see it from here because and this point is capital R. Okay. And the point just after it is R1. So at capital R, we are working with solid cylinder only. So we will be plotting the formulas of solid cylinder, that is sigma 1 or sigma 1 or sigma 2 So the expression of sigma 1 is what? From here we know that the expression is lambda plus mu into C1. So that's why it has been plotted here. Now the sigma theta theta also has the same expression because D1 was 0. So till point R, I will plot slightly below it, but it is the same value just for the clarity because so sigma theta theta. Okay. Sigma theta theta. This is sigma theta theta. And this is sigma R. They are the same plots. Okay. They have been plotted differently just to show you. Now from after this, we will have to use the expressions of sigma theta theta 2 and sigma RR2. So sigma RR2, here it is. So sigma RR2, here we also have this 2 mu D2 R square term. So at R equal to infinity, it will tend to 0. Sorry, it will tend to lambda plus mu into C2. So we have another limiting value here. This value is lambda plus mu into C2. So this curve of sigma RR will be asymptotic to this line at R equal to infinity, and at R equal to R1, if you put at R equal to R1, you will find that sigma RR is will get this value lambda plus mu into C1. Okay. If you put it after solving, you put it there, you will get it. So sigma RR is actually continuous here. So it will be a continuous curve. It will be asymptotic to, let me draw using another line, another color. So sigma RR will be a continuous curve asymptotic to this line. and at infinity this will meet, and this point is R2. Okay. But when you go to plot this sigma theta theta, you will find that sigma theta theta is not continuous. This will be discontinuous. Okay, and here after capital R, we are plotting what? Sigma theta theta 2. So you will find that this graph will also become asymptotic to this line. Okay, at R equal to infinity. Not line, this is also a curve. Sorry for the wording. Oh, not able to pull it. Why? Pencils. So it will be something like this. This is the plot for sigma theta theta. Sigma R R. This is sigma R R. Here it is equal to sigma R R 2. Okay. Here it is equal to sigma R R 1. It is equal to sigma theta theta 1. And here it is equal to sigma theta theta. So I hope this question was this question became clear to you, that what we did in this question. So you can do the calculations, and after that, if you plot these graphs, you will find that you will get this trend. The sigma RR will be continuous and sigma theta theta will be discontinuous. So with this, I'd like to end this session. If any one of you has any doubt, you can ask it right now. You can call, you can write in the chat. Does any one of you have any doubt? If anyone has any doubt, they can ask. They can write in the chat. They can unmute themselves and they can speak. Otherwise, I would leave this session now. So since none of you are asking any questions, I'll leave this question. It's already 8:06 now. So thank you for joining. Next week also, I will take this class on Tuesday from 6 to 8. Okay, from 6 to 8, I will take this class. And I hope to see you again next week. Thanks all of you for joining. Have a great day. Bye.